Hello, I am Milad Ghaznavi from the University of Waterloo. I present our paper, Fault-Tolerant Service Function Chaining, which is a system to provide fault tolerance for a chain of mailboxes. This is a joint work with my colleagues Elahe Jalalpur, Bernard Wang, Rauf Boutaba, and Ali Majdizadeh. Mailboxes are prevalent in enterprise networks serving different functions. Examples of mailboxes are firewall, intrusion detection systems, and NATs. Packets commonly pass through an ordered sequence of mailboxes called a service function chain or simply a chain. The network operation depends on the reliability of the entire chain. Because of their critical operation, mailbox failures are the largest source of high-severity incidents in one data center study. Although they are only 11% of all network devices, they contribute to 43% of high-severity incidents. Their failures have led to major service outages. As a result, there is significant work to build fault-tolerant mailboxes. Their basic idea is to have a backup instance so that upon failure, the traffic is redirected to this instance. In this example, upon the failure of the primary NAT, the traffic is redirected to the backup NAT. Providing mailbox fault tolerance is challenging because the state must be replicated consistently. If the state becomes inconsistent, mailboxes can drop connections, send packets to wrong destinations, or even cause outages. In this example, Alice's connection is dropped due to inconsistent replication. Previous approaches to mailbox fault tolerance fall into two categories. Externalized state approaches, which separate the mailbox state from its logic and store it into a fault-tolerant data store, and snapshot-based approaches, which take and replicate the snapshots of mailbox state. Using existing solutions for chain of mailboxes comes with significant performance overheads. This motivates us to explore another approach to provide fault tolerance for chain of mailboxes. The goals of this approach are providing consistent state replication to tolerate F failures, to minimize the performance overhead during normal operation, and to minimize the disruptions due to failures. To meet these goals, we introduce a new system called fault-tolerant chaining, or FTC. FTC has three main ideas. Internal replication, where FTC uses the chain itself to provide fault tolerance. Transactional packet processing, which simplifies the development of multi-core fault-tolerant mailboxes. And data dependency vectors, which allows FTC to scale up and down mailboxes across the chain independently. Let's have a closer look on FTC's normal operation using in-chain replication to tolerate a single failure. For each mailbox, FTC instantiates a replica. These replicas are co-located in servers hosting mailboxes. The dotted lines shows physical machine boundaries. In addition, FTC adds two other components, a forwarder and a buffer. They communicate to replicate the state of mailboxes at the end of the chain to the servers at the beginning of the chain. FTC components communicate as shown. When a packet arrives, the forwarder piggybacks the state changes of mailbox M3 with the packet and forwards this packet. As the packet passes through the chain, each replica detaches and replicates the state, tracks the state changes made by the mailbox, and piggybacks these state changes onto the packet before forwarding it to the next mailbox of the chain. The buffer releases the packet once the state of mailbox M3 is replicated at the beginning of the chain. This allows FTC to eliminate the need of any dedicated replica servers to tolerate failures. Upon a mailbox failure, FTC selects a server, instantiates a replica. This replica concurrently fetches the lost state, including the state of M1 and M2. Once the state is fetched, FTC instantiates M2. then FTC reroutes the traffic towards and from this new middle box. To support concurrent packet processing, FTC introduces transactional packet processing. Most existing solutions are single-threaded or batch packet processing. FTMB provides concurrent packet processing, however it uses a complex design to track every read and write on any state variable. FTC introduces packet transactions for a simpler design. It tracks the state changes in granularity of packet transactions. It also does not track read-only transactions. FTC also introduces data dependency vectors to capture the partial order of transactions. Compared to conventional approaches that track the operation of threads, FTC tracks data changes. FTC divides the state to multiple partitions and uses a vector of sequence numbers to track the state partition changes. This allows a middle box and its replica to have a different number of threads, while the state replication remains consistent. This provides more flexibility and improves resource utilization compared to existing solutions that require a fixed one-to-one mapping between middle box threads and those of its replica. Furthermore, data dependency vectors allow a middle box to vertically scale by failing over to a server with different number of cores. For evaluation, we compare FTC with NF and FTMB. NF is a non-fault tolerant system with ideal performance. FTMB uses state logging and snapshots to provide middle box fault tolerance. We implement two FTMB versions with the snapshotting on and off. This slide presents the throughput of chains where we vary the chain length and measure the end-to-end throughput. As shown, FTC throughput is largely independent of the chain length. FTC throughput is twice the throughput of FTMB, and FTC achieves 3.5 times higher throughput compared to FTMB with the snapshots. The throughput of FTMB with the snapshots drops by almost 40% due to periodic snapshots taken at all middle boxes of the chain. Providing fault tolerance for a chain of middle boxes is becoming increasingly important. FTC substantially improves the efficiency of existing solution by treating the entire chain as a fault-tolerant unit instead of making individual middle boxes fault-tolerant. FTC introduces two optimizations to improve the operation of a fault-tolerant chain. Using transactional packet processing, FTC provides concurrent packet processing, and using data dependency vectors, FTC provides concurrent state replication. Please see how these mechanisms work in our paper, and for more benchmark including FTC improvement on packet latency.